What is logarithm? The word logarithm was coined by Scottish mathematician John Napier in 1614 by combining the Greek word logos, meaning proportion or ratio, and arithmos, meaning number. In its simplest form, a logarithm answers the question, how many of a number do we multiply to get another number? For example, how many 2's do we multiply to get 16? The answer is 2 into 2 into 2 into 2 is equal to 16. Therefore, we have to multiply 4 of 2 to get 16. Hence, logarithm is 4. We can express this mathematically as log of 16 base 2 is equal to 4. Therefore, 2 into 2 into 2 into 2 is equal to 16 is same as log of 16 base 2 equal to 4. Or 2 raised to power 4 equal to 16 can be transformed to log of 16 base 2 equal to 4. The logarithm tells us what the exponent is. In general, we can say that a raised to power x equal to y implies that log of y base a is equal to x. For example, log of 125 to base 5 is, this can be calculated by finding the exponent to which 5 must be raised to get 125. 5 raised to power 3 is equal to 125. So an exponent of 3 is needed to make 5 into 125 and log 125 base 5 is equal to 3. Therefore, two types of logarithm extensively used in mathematics, log base 10 and log base e. Sometimes logarithm is written without base like log 100. This usually means that base is 10. Therefore, log 100 is equal to 2. This is known as common logarithm and is extensively used by engineers. Another base which is often used is Euler's number e, which is equal to 2.71828. This is known as natural logarithm and is generally written as ln. For example, ln2 is equal to log of 2 base e, which is equal to 0.693, which means that 2.71828 raised to power 0.693 is equal to 2. All of our examples have used whole number logarithms like 2 or 3, but logarithms can have decimal values like 2.5 or 6.081, etc. For example, log 10 base 10 is equal to 1 and log 100 base 10 is equal to 2. Therefore, for log of all the numbers between 10 and 100 must lie between 1 and 2. For example, log of 26 base 10 is equal to 1.41. As logarithm deals with multiplication, negative logarithms deal with divisions. A negative logarithm means how many times to divide by the number. For example, what is log 0.008 base 5? Which is 1 divided by 5 times 5 times 5 equal to 0.008. Or 5 raised to power minus 3 is equal to 0.008. Therefore, log of 0.008 base 5 is equal to minus 3. Let's look at this table of base 10 logarithms. Multiplying and dividing are all part of the same simple pattern going from negative to 0 to positive numbers.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel. For more interesting and educational videos to earn while you learn, download Extraclass app from Google Play Store and get rewarded for study.
How to find domain of a logarithmic function. Mathematically, logarithm is written like this and read as log of x base a, where x is known as the argument and a is the base of the log. According to the definition of logarithm, value of x and a is always greater than 0 and a is not equal to 1. Therefore, the value of a are divided into two intervals. First, when a greater than 0 but less than 1. Second, when a greater than 1. From the basic understanding of definition, one must ask why base of the log function cannot be equal to 0, 1 or negative. Let's try to understand the result when we take the base as 0 and argument values as 4, 5, 6 with corresponding log values as b, c and d respectively. So by definition of log, 0 to the power b is 4, 0 to the power c is 5 and 0 to the power d is 6. We can simply observe that in either of the three cases, left-hand side cannot be equal to right-hand side, because 0 raised to the power any number is always equal to 0. This rule is contradicted if the base of log is taken as 0. Therefore, log to the base 0 not possible. In the case where base value is equal to 1, the value of argument automatically gets restricted to 1, since 1 to the power of any number is always 1, which contradicts the definition of functional equation. Therefore, we cannot have the base value of a log function as 1. Negative value of base are not considered to avoid confusion between positive and negative outputs. Now, using these conditions of log, we can easily proceed to find the domain of a logarithmic function. Let's take an example to understand the method of finding domain of log functions. Question: find the domain of the function f of x is equal to log 5x minus x square whole divided by 4 with the base 10 whole power 1 by 2. Options are given and we have to choose the correct one. Solution: in the given problem, the function is square root of log 5x minus x square divided by 4 with the base 10. To find the domain of the function, we have to find the values of x which define the given expression. If we closely observe, the given expression contains two functions, log inside a square root. Therefore, we will find domains for each of these and then take the intersection to get final domain. According to the definition of log, the value of argument must be greater than 0. When we take argument 5x minus x square divided by 4 greater than 0, we have 5x minus x square greater than 0, or x squared minus 5x less than 0. From this expression, we get the domain value of x lying between 0 to 5. Now, the overall function is only defined when the value inside the square root function is greater than or equal to 0. Therefore, log 5x minus x squared divided by 4 with the base 10 is greater than equal to 0, or 5x minus x squared divided by 4 greater than equal to 1. On simplification, we have x squared minus 5x plus 4 less than equal to 0. This is a quadratic equation which has two factors, 1 and 4. Here we get x greater than equal to 1 and less than equal to 4. When we take common intersection of both the domain conditions, we get x greater than equal to 1 and less than equal to 4. Hence, the domain of the given function is option B.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel for more interesting and educational videos to earn while you learn. Download Extraclass app from Google Play Store and get rewarded for studying.
How to solve problems based on logarithmic properties? Question: if 3 to the power x equal to 4 to the power x minus 1, then x is equal to? The options are. This question was asked in JEE Advanced 2013 exam. Since all the given options have logarithmic terms, so it is obvious that logarithmic properties will be used. Solution: The given equation is 3 to the power x equals to 4 to the power x minus 1. Let's take log on both sides of the given equation with base 3. Using the log property, log of b to the power c with base a equal to c log of b with base a. We can write x into log of 3 with base 3 equals to x minus 1 into log of 4 with base 3. Or x into log of 3 with base 3 equals to x minus 1 times 2 log of 2 with base 3. Or x equals to 2x log of 2 with base 3 minus 2 log of 2 with base 3. Or x equals to 2 log of 2 with base 3 upon 2 log of 2 with base 3 minus 1. Or it can also be written as x equals to 1 upon 1 minus 1 by 2 log of 2 with base 3. Or x equals to 1 upon 1 minus 1 by log of 4 with base 3. Using the log property, log of b with base a equals to 1 by log of a with base b. We can write x equals to 1 upon 1 minus log 3 with base 4. We can also write this expression as x equals to 1 upon 1 minus 1 by 2 log of 3 with base 2. Using this property, we can write x equals to 2 upon 2 minus log 3 with base 2. Thus, option A, B and C are the correct answers.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel. For more interesting and educational videos to earn while you learn, download Extraclass app from Google Play Store and get rewarded for studying.
What is fundamental logarithmic identity? Say x is equal to log of m to base b is a given logarithmic equation. By the basic definition of logarithm, this can be also written as b raised to the power of x is equal to m. Replacing this value of x in the exponent of b by the original value that we have assumed earlier, we get b raised to the power log of m to base b is equal to m. This particular way of representing a logarithmic equation is called the fundamental logarithmic identity. The reason this is called an identity is pretty simple and straightforward, pertaining to same reasons why any equation is called an identity in the first place. Any identity equation is that equation which stays true irrespective of the input, which means that whatever value be plugged into the variable, the output will always be true for that particular equation. This expression that we have derived here is also an identity, which means whatever be the restricted values of b and m within their domain, output will always be m. For example, 2 to the power log of 13 to base 2 will always be 13. Again, 3 to the power log of 5 to base 3 is 5. 4 to the power log of 70 to base 4 is 70. Three important deductions can be made from this important identity. First, log of n to base n is 1, which can be interpreted as when the number and base are same, then the value of logarithm is 1. Second, log of n to base 1 by n is equal to log of 1 by n to base n, whose value is always minus 1, which can be interpreted as when the number and base are reciprocal to each other, then the value of logarithm is always minus 1. Third, log of 1 to base a is always 0, provided that a is greater than 0 and not equal to 1, following the basic definition of logarithm. This is always true because anything to the power 0 is 1, so log of 1 to base a is 0. The reason why a is not equal to 1 is because log of n to base 1 is meaningless, since 1 to the power of anything will always be 1, thus eradicating the possibility of representing different numbers. Also, if n is equal to 1, then log of 1 base 1 will have infinitely many solutions and will not be unique, which is necessary in functional equation. Thus, we have learned to write fundamental logarithmic identities and have learned important deductions based on it, which must be remembered while solving questions related to logarithms. Now, let's solve a question based on its application. Question: find the range of x satisfying the inequation x to the power log of 10 to base x multiplied by log of x to base 10 is less than 1. Solution: we can see that the first term in the LHS is a direct application of the fundamental logarithmic identity. Thus, x to the power log of 10 to base x is 10 itself. Using it, we can simplify the inequation to 10 into log of x to base 10 is less than 1, which can be arranged in the form log of x to base 10 is less than 1 by 10. Let us call this equation number 1. Since powers of the same base are comparable, let us write equation 1 in the power of 10. Reason being, we can see that 10 to the power log of x to base 10 can again be simplified using fundamental logarithmic identity. Thus, we get x is less than 10 to the power 1 by 10 or 0.1. Now, in this question, x is given in the base, hence x should be greater than 0 and not equal to 1. So, the final range of x would be x belonging to 0 to 10 to the power 1 by 10 except 1.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel. For more interesting and educational videos to earn while you learn, download Extraclass app from Google Play Store and get rewarded for studying.
How to compare two logarithmic values. Comparing any two arbitrary values, say a and b, gives rise to three possibilities, namely a greater than b, or a less than b, or a equal to b. This is also known as trichotomy. Similarly, two unique logarithmic expressions must be related to each other by trichotomy. The one condition to be kept in mind is that logarithms of same bases are only comparable where the base is greater than 1. Proof: say we are given two numbers a and b such that a is greater than b. Taking log on both sides to the base c, the inequality sign will not change. Hence we get log of a to base c is greater than log of b to base c. So, we are given an inequality on two numbers. The logarithms on same bases hold the same inequality, where the base is greater than 1. This process works both ways. That is, if a logarithmic inequation is given on the same base, then their arguments hold the same inequality as the logarithm. Let's solve an example to clarify this concept. Question: state whether the following inequality is true or false. Log of 5 to base 3 is greater than log of 25 to base 17. Solution: here the expressions do not have same base, so they are not comparable at the moment. To force a comparison, we need to express both the logarithmic terms in same base. This can be achieved if we look closely for some connection in between the two expressions. We can see that the arguments in both the expressions are multiples of 5. So, our basic intuition says we need to express both the expressions to base 5. Before that, we have to achieve 5 on both the terms. So, using the exponential property, log of 25 to base 17 can be written as log of 25 to power half to the base 17 power half, which is same as log of 5 to base root under 17. Using the reciprocal property that we have learned while learning base change theorem, where log of a to base b is same as 1 divided by log of b to base a, we can rewrite the inequation as 1 divided by log of 3 to base 5 is greater than 1 divided by log of root under 17 to base 5. Here, both the terms are surely positive, since their corresponding arguments and bases are on the same side of unity. Now, if we recall, the inequality sign of a given inequation consisting of two positive numbers reverses if their reciprocals are compared. That is, if 2 is greater than 1, then 1 divided by 2 must be less than 1, which is true. So taking reciprocals of the original expressions, we get log of 3 to base 5 is less than log of under root 17 to base 5. Finally, the given logarithmic inequation is now expressed in the same base 5. Since 3 is less than root under 17, so the logarithms on same base 5 must also hold the same inequality. So, log of 3 to base 5 must be less than log of root under 17 to base 5, which is the same as our derived equation. So the given inequation is true. Thus, we have learned how to compare two logarithmic expressions.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel. For more interesting and educational videos to earn while you learn, download Extraclass app from Google Play Store and get rewarded for studying.
What are the principal properties of logarithm? Like a lot of functions, the logarithmic function also comes packed with a flock of properties that eventually help us to solve logarithmic equations easily and tactfully. There are four main types of principal properties of a logarithm. Property 1. Product rule of logarithm. Two numbers in product form when expressed in their logarithmic forms are added instead of getting multiplied. For example, say two numbers m and n are multiplied to form their product p. Taking log on both sides with base 10, we get log of p is equal to log of m into n. According to this property, this expression can also be written as log of m plus log of n. We should make sure that the base in each logarithmic expression must be same, just like it is 10 in this case. For proving this, let us consider the logarithmic terms log of m equal to x1, log of n equal to x2, and log of mn equal to x3. From basic definition of logarithm, we get 10 to the power x1 equal to m, 10 to the power x2 equal to n, and 10 to the power x3 equal to m into n. Replacing the respective values of m and n in RHS of the third equation, we get 10 to the power x3 is equal to 10 to the power x1 into 10 to the power x2, which is same as 10 to the power x1 plus x2. Since powers of the same numbers are comparable, we get x3 equal to x1 plus x2. Replacing back their original values, we get the first property of logarithm. Property 2. Quotient rule of logarithm. This property is similar to the product rule. Here, if two numbers are in quotient form from their logarithmic expressions are subtracted. Specifically, the terms in the denominator are subtracted from the terms in the numerator. Say q equal to m divided by n. Then log q, which is equal to log of m divided by n, can be written as log of m minus log of n. Its proof is similar to that of the product form, and this is evident from the fact that logarithm is another form of expressing exponents of a number. Just like in logarithm, when a number is multiplied by itself, its exponents are added, and when divided, the exponents are subtracted. These properties have no restrictions on their usage. That is, these properties can be generalized far more than two numbers. For example, log of mn divided by op to the base a can be written as log of m plus log of n minus log of o minus log of p. We must make sure that all the logarithmic expressions are expressed in the same base as the original expression, that is a. Property 3. Exponent rule of logarithm. In this property, any power appearing in the argument of the logarithm is shifted and multiplied with the logarithm itself. For example, log of m to the power x to base a is same as x times log of m to base a. Here, if we observe carefully, we can see that the exponent x is shifted from the power form to multiplication form. This process works both ways, meaning that if we are given an expression x times log of m to base a, we can rewrite it as log of m to the power x to base a. Property 4. Exponent of base. In this property, any exponent appearing in the base of the logarithm is shifted and its reciprocal gets multiplied with the logarithm itself. For example, log of m to base n to the power y can be rewritten as 1 by y multiplied by log of m to base n. If we observe the two properties carefully, we can see that exponents in the argument get multiplied to the logarithm while powers in the base are directly used to divide the logarithm. These two properties can also be used simultaneously, that is, log of m to the power x to base n to the power y can be rewritten as x divided by y into log of m to base n. Let's solve an example based on the application of properties of logarithm. Question. Solution. The simple approach will be to break down every argument as a product of 3 and some other number, and then by using property 1, we can separate the terms. So the big expression can be rewritten as shown. Let log of 3 to base 2 be taken as x. Simplifying, we get the expression as shown. Multiplying x with x plus 6 and x plus 4 with x plus 2, we get the following result. Taking x squared plus 6x common, we can see that the term inside the square root is a perfect square of x squared plus 6x plus 4. On simplification, we get the value of the expression as 6. This concludes our video on principal properties of logarithm. Students must remember these 4 properties and apply them while solving problems. In the next video, we will study base change theorem in detail.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel. For more interesting and educational videos to earn while you learn, download Extraclass app from Google Play Store and get rewarded for studying.
How to determine whether a given logarithmic expression is rational or not. Any rational number can be written in the form of p divided by q, where p and q are co-prime natural numbers. Co-prime means p and q are relatively prime to each other, or that their highest common factor HCF is equal to 1. Do remember that for two integers to be co-prime, they need to be prime numbers themselves. For example, 4 and 5 are co-prime integers, but 4 is not a prime number. Yet, 4 divided by 5 is a rational number in its lowest form. Now, in order to determine whether a logarithmic expression, say log of x to base a, is rational or not, we will use the method of contradiction. In this method, we will first assume that the given logarithmic expression is rational and hence equate it to p divided by q. From basic definition, we can write a to the power p divided by q equal to x. Now, we will simplify the expressions on either side of equality and look for its feasibility. If the equation seems feasible for certain values of p and q, then our assumption would be correct and the given logarithmic expression will give a rational value. Otherwise, if the equation does not seem feasible for any value of p and q, then our assumption would become incorrect and the given logarithmic expression will give an irrational value. Let us take an example to clear our conceptual understanding. Question. Prove that log of 9 to base 2 is irrational. Solution. Let us assume that the given expression is rational, that is log of 9 to base 2 is equal to p divided by q, where p and q are natural co-prime numbers. From basic definition of logarithm, we can write 2 raised to the power p divided by q is equal to 9. Raising both sides of equality to the power q, we can write 2 to the power p is equal to 9 to the power q. Now, 2 to the power p is same as 2 into 2 into 2, multiplied p times, and 9 to the power q is same as 9 into 9 into 9, multiplied q times. We can easily observe that the value on left-hand side is even, while the value on right-hand side is odd. But this is not possible because an even expression can never be equal to an odd expression. Hence, we are sure that our original assumption of the given logarithmic expression to be rational is wrong. Therefore, the given logarithmic expression is an irrational number. Hence proved. Students must follow similar methodology to determine if a given logarithmic expression is rational or not.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel. For more interesting and educational videos to earn while you learn, download Extraclass app from Google Play Store and get rewarded for studying.
How to solve simple logarithmic equations? To solve any logarithmic equation, we would need to keep all of the logarithmic properties at the tip of our fingers, starting from definition, fundamental logarithmic identity, product property, quotient property, power properties, and the base change theorem. Let us solve an example based on these properties. Question: 2 log of x minus 7 divided by x minus 1 to base 2 plus log of x minus 1 divided by x plus 1 to base 2 equal to 1. Solution: if we look closely, we can rewrite the equation as log of x minus 7 divided by x minus 1 whole squared to the base 2 plus log of x minus 1 divided by x plus 1 to base 2 equal to 1. Since both the terms have same base 2, we can use the product property to simplify the equation to log of x minus 7 squared divided by x minus 1 into x plus 1 to base 2 equal to 1. From the basic definition of log, we get x minus 7 whole squared divided by x minus 1 into x plus 1 equal to 2. On further successful simplification, we get two values of x which are minus 17 and 3. But this is not our final answer. We must always check whether the solution obtained are within their domain or not. If we check for x equal to minus 17, we can observe that it satisfies the argument of restrictions of both the terms. But for x equal to 3, argument in the first term becomes negative, which defines the definition of logarithm, so we need to reject 3. So, our final answer is x equal to minus 17. Now, we need to learn how to take log on both sides of an equation. Say, an equation y equal to x to power log of 2 to base 3 is given. In order to take log on both sides, all we need to do is to write log on both sides, keeping the terms of the original expression in the argument of logarithm, and choose a relevant base according to convenience. Since here a logarithmic term with base 3 is already present, we will take the base of the logarithm as 3 for simplicity. So our equation will turn into log of y to base 3 is equal to log of x to the power log of 2 base 3 to whole base 3. Using the power property of logarithm, we can simplify the expression to log of y to base 3 equal to log of 2 to base 3 multiplied by log of x to base 3. Let's solve another question based on these simple logarithmic properties. Question: 3 to the power log of x to base 3 whole squared plus x to the power log of x to base 3 equal to 162. Solution: since powers are multiplied in the first term, we can rewrite the equation as 3 to the power log of x to base 3 whole power log of x to base 3 plus x to the power log of x to base 3 equal to 162. Using fundamental logarithmic identity, the first term simplifies to x to the power log of x to base 3, which is same as the second term on the left-hand side. Therefore, the equation simplifies to x to the power log of x to base 3 equal to 3 to the power 4. In order to further simplify, now we need to take log of base 3 on both sides of the equation. Therefore, we get log of x to the power log of x to base 3 to whole base 3 equal to log of 3 to the power 4 to base 3. Using power property of logarithm, we get log of x to base 3 whole squared equal to 4 into log of 3 to base 3 on the right hand side, which is equal to 4. Further simplifying, we get two values for log of x to base 3 as plus minus 2, which is same as x equal to 3 to the power 2 and 3 to the power minus 2, which gives us two values of x, namely 9 and 1 by 9, both of which are well within the defined domain of the function. Thus, our video on logarithmic equation has come to a conclusion.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel for more interesting and educational videos to earn while you learn. Download Extraclass app from Google Play Store and get rewarded for study.
How to graph a logarithmic function. Before learning this, let us first understand why do we need to learn to graph any function. Practically, drawing a rough sketch of a function aids in remembering the definition and properties with visualizations rather than mugging them up. Now, since every logarithmic function of the form y equal to log of x to base b is the inverse of an exponential function with the form y equal to b raised to the power x, hence their graphs will be reflections of each other across the line y equals to x. So, if we have two graphs of f of x equal to 2 raised to the power x and g of x equal to log of x base 2, we can see that the x and y coordinates are reversed in either graphs. We can compare the two graphs based on the following points. Number 1. Intercept. Y-intercept of f of x at 0, 1 is the reflection of x-intercept of g of x at 1, 0. Number 2. Domain and range. The domain of f of x is the same as the range of g of x and varies from minus infinity to plus infinity. The range of f of x is the same as the domain of g of x and varies from 0 to infinity. Now, if we consider the parent logarithmic function f of x equal to log of x to base b only for any real number x and base b greater than 0 and not equal to 1, we can observe the following characteristics from the graph. It is a one-to-one function, meaning every value of x gives a distinct and unique value of y. Domain of the function vary from 0 to infinity and range varies from minus infinity to plus infinity. The graph has x-intercept 1 and no y-intercept with a key point at b, 1. Moreover, the graph is increasing when b is greater than 1 and decreasing if b is less than 1. With both graphs having an asymptote at x equal to 0, meaning both the graphs converge towards infinity at x equal to 0. Now, let's move on to learn the method of transforming logarithmic graphs starting from the parent function. Like most functions, we can shift, stretch, compress, and reflect the parent function without loss of shape. First, transformation, horizontal shift. When a constant c is added to the input of the parent function f of x equal to log of x to base b, the result is a horizontal shift, c units in the opposite direction of the sign of c. When a constant c greater than 0 is added to the input of the parent function, the graph is shifted alongside left, and when c is subtracted from the input, the graph is shifted alongside right. Second transformation, vertical shift. When a constant d greater than 0 is added or subtracted to the parent function, the result is a vertical shift d units in the direction of the sign on d. When d is added to the parent function, the graph is vertically shifted up by d units, and when d is subtracted from the parent function, the graph is vertically shifted down by d units. Third transformation, stretch and compression. When the parent function multiplied by a constant, the result is a vertical stretch or compression of the original graph. When a constant a, say greater than 1, is multiplied to the parent function, the transformation is a vertical stretch. Similarly, when the parent function is divided by the same constant, the transformation is a vertical compression. Fourth transformation, reflections. When the parent function is multiplied by -1, the result is a reflection about the x-axis, and when the input is multiplied by -1, the result is a reflection about the y-axis. First, let us restrict the base b to be greater than 1. Now we can see that the graph undergoes reflection about the x-axis when the parent function is multiplied by -1. Similarly, the graph will undergo reflection about the y-axis when the input is multiplied by -1. Thus, we can observe that in both the cases, the new transformed function changes its monotonicity, that is, being monotonically increasing, it transforms into a monotonically decreasing graph. Keeping the visual changes of all these four transformations in mind will help us in graphing any logarithmic function.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel. For more interesting and educational videos to earn while you learn, download Extraclass app from Google Play Store and get rewarded for studying.
What is monotonicity of logarithm? In general, a logarithmic function is a monotonic function, varying from -infinity to infinity. Whether it is monotonically increasing function or a decreasing one mainly depends on the value of the base. Let us assume a logarithmic function y equal to log of x to base a, where a is greater than 0 and not equal to 1, and the domain x is positive. Thus, a logarithmic function is divided into two main sections. We are going to take the help of exponential function to help in the following observations. Case 1. When base a is greater than 1, here let us further break down the function based on its domain into two parts, namely, when x is less than equal 1 and when x is greater than 1. When x is less than 1 and starts approaching 0, by the basic definition of logarithm, we can see that a to the power y tends to 0 too. The only way possible to make this positive number tend to 0 is when y tends to -infinity. For x equal to 1 and a, the value of logarithm comes out to be 0 and 1 respectively. Also, we can observe that for x greater than 1, when x approaches positive infinity or a to the power y tends to positive infinity, y also tends to positive infinity. Based on the above deductions, graph of the logarithmic function with greater base than 1 can be drawn easily. Case 2. When base a is less than 1, that is, when a ranges from 0 to 1, here also we will break it down to two parts, namely for x less than 1 and x greater than 1. When x is less than 1 and starts approaching 0, by the basic definition of logarithm, we can see that a to the power y tends to 0 too. The only way possible to make this positive number tend to 0 is when y tend to positive infinity. Since both x and a are less than 1, so x will be equal to a in this region only, and y will be equal to 1. And when x will be equal to 1, then y will be equal to 0. Similarly, for x greater than 1, as x approaches infinity, the value of logarithmic function will tend to -infinity. Based on the above deductions, graph of the logarithmic function with base less than 1 can be drawn easily. Now, let us compare the two graphs. We can see that when the base and the domain of logarithm are on the same side of unity, the value of the logarithmic function is always positive. When base is greater than 1, the logarithmic function takes positive values only when x is also greater than 1. Similarly, when base is less than 1, the logarithmic function takes positive values only when x is also less than 1. Remembering this particular property is beneficial for solving equations involving logarithmic functions.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel. For more interesting and educational videos to earn while you learn, download Extraclass app from Google Play Store and get rewarded for studying.
What is characteristic and mantissa of a logarithmic number? To understand this concept, first we need to know how to write a positive number in its standard form. For example, 210 is written as 2.1 into 10 raised to the power 2. 0.007 is written as 7.0 into 10 raised to the power minus 3. If we observe closely, we can see that in its standard form, a positive number has only one digit before decimal and everything else gets embedded into the power of 10. From this we can say that a positive number n can be expressed in standard form as a into 10 raised to the power b, where a belongs to 1 to 9 and b is any integer. Taking common log on both sides of this equation, we get log n to base 10 equal to log a base 10 plus log of 10 to the power b to base 10. On further simplification, we get log n equal to log a plus b. Here b represents the integral part of log n and is known as characteristic of number n. Log a represents the non-negative fractional part of log n and is known as the mantissa of number n. Now, having learnt the basic meaning of characteristic and mantissa, let us discuss its use. This concept is mainly used to count the number of zeros to the left and right side of decimal point respectively. For a number greater than 1, number of digits before decimal is given by b plus 1. For example, 1729 can be written as 1.729 into 10 to the power 3. Comparing with standard form, we get b equal to 3. So the number of digits before decimal place should be equal to b plus 1, that is 4. And for the number 1729, it is true. For a number less than 1, number of zeros to the right of decimal point before significant digit starts is given by minus b minus 1. For example, for the number 0.01729, which in its standard form will be written as 1.729 into 10 to the power minus 2, so value of b is minus 2 here. Therefore, number of zeros before significant digit starts is minus of minus 2 minus 1, that is 1, which we can see to be true since there is 1 0 before the first significant digit, which is 1 here. Let us solidify our understanding of this concept with the help of some examples. Question: find the number of digits in 6 raised to the power 50. Solution: it is evident from the question that the number of digits before decimal is asked in this question. Taking log of the number, we get log of 6 to the power 50 equal to 50 times log 6, which is equal to 50 times log 2 plus log 3. Putting the respective values of log 2 and log 3 and simplifying, we get the final value as 38.905, which can be broken down into 38 as the integral part and 0.905 as the fractional part. Comparing this with the standard form expressed in log form, we get the integral part, that is 38, as characteristic and the fractional part 0.905 as mantissa. Since the given number is greater than 1, therefore number of digits before decimal point is given by 38 plus 1, that is 39. Let us solve another question. Question: find the number of zeros before a significant figure starts in 3 to the power minus 50. Solution: taking log of the number, we get log of 3 to the power minus 50 is equal to minus 50 times log 3, which comes out to be minus 23.805. Adding and subtracting 1 to this number, we get minus 24 plus 0.195. The reason we need to do this step is because we need to express the logarithm of the given number in our general form containing characteristic and mantissa, which is the fractional part, cannot be negative according to definition. Comparing the standard log form, we get the integral part as minus 24 and fractional part as 0.195. Since the given number is less than 1, so number of zeros after decimal before significant figure starts can be calculated by minus of minus 24 minus 1, which is 24 minus 1 or 23. If we compare both the examples, we can see a striking relation between a number and the characteristics of its log. For a number greater than 1, characteristic is positive, while for a number lying between 0 and 1, that is a fractional number, its characteristic is negative. Summarizing, we have learned that every positive number n can be expressed in its standard form as a into 10 to the power b. Common logarithm of a number expressed in this form is written as log a plus b, where b is an integer and is known as the characteristic of logarithm, and log a, which represents the non-negative fractional part, is known as the mantissa of the logarithm.
Please like, share and comment on the video, and don't forget to subscribe to our YouTube channel. For more interesting and educational videos to earn while you learn, download Extraclass app from Google Play Store and get rewarded for studying.